statement of all elementary steps. An elementary step has one transition state and no intermediates. The sum of all the elementary steps constitutes what we call a reaction mechanism. So here is an example of a reaction mechanism associated with the formation of the ozone hole. Here is elementary step 1. Here is elementary step 2. The sum of these two reactions gives us the overall reaction. In this first step, chlorine acts as a catalyst. Chlorine monoxide is the intermediate. And the overall reaction does not contain the intermediate or the catalyst. We then talked about molecularity. Molecularity applies only to elementary steps. Those reactions that take place via one transition state and one intermediate. So, and no intermediate, sorry. Okay? So the concept of molecularity does not apply to complex reactions. It applies only to elementary steps. If the number of molecules involved in an elementary step is 1, then we say that it's a unimolecular reaction. The differentiated rate law is K times A to the power 1. If 2 molecules are involved in an elementary step, we say it's a bimolecular reaction. And the differentiated rate law is K times A times B. So if you have a unimolecular reaction, you have a first order reaction. If you have a bimolecular reaction, you have a second order reaction. But the converse is not true. If you have a second order reaction, that does not necessarily mean that it is a bimolecular reaction. Very important distinction. Termolecular reactions are very, very rare because the probability of 3 molecules coming together at the same time with the right energy, with the right orientation to form a product is very, very unlikely. So how do we go about determining reaction mechanisms, which is one of the central goals of chemistry, to figure out what are the individual steps that make up a chemical reaction? What you do is you do experiments. Let me make this a little bit clearer here. You do experiments to determine the rate law. What I mean by determining the rate law is to determine for this reaction here, minus dA dt 1 over A is equal to K times A to the power X B to the power Y. So this is what I mean when I say do experiments to determine the rate law. Determine the value of K, X, and Y. When you do that, you have now obtained the differentiated rate law. Then you devise a mechanism. This is trial and error. You guess. And then once you guess a mechanism, because the mechanism is made out of elementary steps, you can deduce what the rate law should be for that mechanism that you proposed. So you can predict the rate law for that mechanism. Then you compare what you predict with what you got here for X, Y, and K. If they agree, then you look for additional experimental evidence, such as the identity of an intermediate. For example, if you're looking at the depletion of ozone catalyzed by chlorine, your mechanism is proposing chlorine monoxide as an intermediate, then it would be very nice to be able to spectroscopically identify this intermediate in that reaction, in which case you can say to a high probability that the mechanism that you're proposing is a reasonable mechanism. So that's what I mean by look for additional supporting evidence. If the predicted rate law does not agree with the experimental rate law, then you come up with a different mechanism. You propose a different mechanism. You guess a different mechanism. It's a trial and error method. There is no set of rules that will apply to every situation. But there are some rules that you can exploit, such as when you add up the elementary steps, the sum should equal the overall reaction. If it doesn't, then you got something wrong. If your elementary steps are consecutive reactions, and if you have one elementary step that is very slow, then the overall rate order, the overall rate equation must be identical to that of the overall reaction. Sorry, let me repeat that. If you have a slow step, the rate law for that slow step is going to be the rate law for the overall reaction. Okay? Those are two of the simplest rules that you're going to learn in this course. There are many, many more rules that you will learn in your first semester physical chemistry course. But for now, we're going to leave it at that. Yes, Laura?
So the only way we'd know what the slowest step was is if we saw that and it included two reactants or products from one specific part.
Right, if in the elementary steps that you're proposing,
yeah,
one of those elementary steps had a rate law that matched this, then, you know, it's reasonable to expect that that elementary step is the slowest step.
Like that example that we had in our outline. So that's the only way we know it's the slowest.
Yeah, again, it's all trial and error. Okay, it's very difficult to say this is the mechanism. You can most often only say this mechanism is consistent with the experimentally observed rate law. You cannot prove a mechanism beyond a shadow of doubt. Okay? Yes? So,
you said that the molecularity is not for the complex reactions, but can complex reactions be broken up into the elementary steps?
right.
And that's always true?
Yeah, I mean, complex reactions can be broken down into elements.
Okay.
That's what defines a complex reaction.
Okay.
Yeah. And so again, let me illustrate the concept of a rate determining step. The honeypots are coming from the left here, and oh, wait. Now I'm getting confused.
You said last lecture.
No, they're going from left to right.
Yeah.
Yeah, they're coming from the woman on the left is working.
Yeah, okay, yeah, it's coming from left to right. Okay, so this woman here is working very hard and producing lots of honeypots. But this woman is working very slow and it's not going anywhere. So the rate of production of honeypots out here is not determined by this woman, but is determined by this woman. If you understand this diagram, you understand the concept of rate determining step. The final thing that we are going to talk about is how does the rate of a reaction change with temperature. Most often what you find is that when you plot the rate of a reaction R as a function of temperature, it shows this behavior. This has been known for over 100 years. Rate as a function of temperature. Yes?
I have a question about that diagram.
Uh-huh.
What if there's someone working after her and like, so wouldn't the rate depend on like whether that person's going like really, really fast or really, really slow?
Yeah, I mean, if there's another person working, to the right of her, and she's slower than her, then that person is going to be the rate determining step. So I'm only assuming there are 2 steps here in this process.
Okay, what
If she's faster, then she's only getting the jars at the rate that the slow woman is passing them off. So she couldn't go faster than the slow woman because she just won't have the jars.
Oh, right, yeah. Okay, sorry.
Very good. So this is what you find typically for a reaction. And one of my students today is going to be talking about a case where this is not what you find. Okay? But the equation that describes this behavior is called the Arrhenius equation. Rate constant is equal to the pre-exponential factor e to the power minus E sub A over RT. E sub A is the activation energy, R is the gas constant, and T is the temperature expressed in Kelvin. Okay, we'll talk about all of this today. Okay, so did we do this question here?
No.
Okay, all right, so let's look at this question. So this is the overall reaction. NO2 plus CO going to NO plus CO2. And here is the experimentally observed differentiated rate law. So this is a first order, second order, or a third order rate law. Second order rate law because it's to the power 2. So is this reaction an elementary step? How do we know that it's not an elementary step? Alice?
If it was, then we would have a, instead of NO2 squared, it would be NO2 times the concentration of CO.
Right. If this was an elementary step, you can immediately write down what the rate law is going to be, and that would be K times NO2 times CO. So the rate law would be K times NO2 times CO. But it's not. Somebody said something. No. Okay.
Wait, why does it have to be that?
Because if this is an elementary step, then if you double the concentration of NO2, the rate doubles. So it's NO2 to the power 1. Same here, this is 1 CO, so it's CO to the power 1. By looking at the elementary step, looking at the stoichiometric coefficients, you can immediately put down what the exponents are going to be. Only true for an elementary step. You cannot do this for a complex reaction. So this is the rate law if this was an elementary step. But the rate law is this. Therefore, this is not an elementary step. So now you're told that the first step is NO2 plus NO2 going to NO3 plus NO. So that's the first step. The second step, when added to the first step, must give you what? The overall reaction. So if I have two NO2s on the left-hand side and I have only one NO2 on the left-hand side in the overall reaction, then what must the second step be? I should have a CO2 on the right-hand side, right? Okay, I have a CO2 on the right-hand side. I should have an NO2 on the right-hand side so that it'll cancel with the NO2 on the left-hand side. Now, NO3 is not in the overall reaction, so NO3 must be on the left-hand side. It must be an intermediate, so it must be used up. And the only other molecule that's missing is CO. Questions? So this is step 1, this is step 2. So which is the rate limiting step?
This one, first one.
The first one, because as soon as you write this elementary step, you can write that the rate is going to be equal to K times NO2 squared. Because this is an elementary step, you can immediately write down the rate law. This rate law exactly matches this rate law. So, therefore, the first step must be the slow step, and the second step must be the fast step.
Wait, how do you know that again?
How do you know?
That one is the slow step.
We look at the rate law. The rate law matches with the overall rate law,
Oh, okay.
And
therefore that must be the slow step. Yes,
can you
Erica.
just go over one more time how you went from step 1 to step 2?
All I'm doing is, if you want, what you can do is take that reaction, there, and from that subtract.
Okay.
Yeah. All right. Questions? All right. So here is the experimental observation, the rate constant plotted as a function of temperature. Remember, the rate constant is lowercase k. Uppercase K is the equilibrium constant. All right? Another way to say this, and this is more crude, is to say that typically reactions double in rate for every 10 Kelvin increase in temperature. But the bottom line is that for most reactions, the rate increases because the rate constant increases with temperature. So look at this example here. The rate increases with temperature, not because the concentrations increase with temperature, but rather because the rate constant increases with temperature. So we're looking at how does the rate constant depend on temperature. That tells us how does the rate depend on temperature. And this is a purely empirical formula. That means that when this equation was written down by Arrhenius, who also was the first person who realized the potential for global warming, this was in 1890. He made some predictions about global warming based on carbon dioxide in the atmosphere. He came up with this equation purely based on experimental data. He had no theoretical basis for writing this equation down. Our entire lecture on Wednesday is going to be on trying to understand what is the theory behind this equation. Why does the rate constant depend on temperature in a manner given by this equation? For now, for today, all we care about is how do we manipulate this equation, not about where did we get this equation. Okay, we will talk about where did we get this equation in class on Wednesday. So A is called the pre-exponential factor or the frequency factor. E sub A is the activation energy. That's the minimum amount of energy required for two reactant molecules to be able to react. If two molecules collide with an energy below the activation energy, they just bounce off each other. R is the gas constant. If we take the natural log of both sides, what do we get? What do we get on the left-hand side? ln of k is equal to ln of A minus E sub A over RT. So if we want to look at how does K depend on T, and if we want to create a straight line, we say this is equal to y is equal to mx plus b. So what is y going to be equal to? Y is going to be equal to?
K. ln K.
ln K. Okay, we want to get a straight line, so we want to use this entire quantity as our y. And what do we want x to be?
T.
1 over t. Okay, because we have 1 over t here. So let me rewrite this equation. This becomes that's 1 over t. So therefore this is 1 over t. So is the graph going to slope this way or is it going to go this way? Let's say this is 1, this is 2. Can you talk to your neighbor and convince your neighbor that you're right and your neighbor is wrong?
I don't know. That graph is really familiar. It reminds me of the exothermic endothermic.
Yeah.
That's what I was thinking.
Yeah.
But they're different. Because that one's different.
There is some relationship, but
1 over
don't-
t.
Don't think of that.
Wait, that
Yeah.
one was equilibrium.
Yeah.
Right, log of K.
Yeah, so I'm just kind of like, oh no, I'm so confused. But,
And the answer in one voice is 1. Okay, when we looked at ln K versus 1 over t, you could have both possibilities. Because what? What is the slope here when you're plotting the natural log of the equilibrium constant versus 1 over t? Negative delta H over R. Delta H could be positive or negative. So the slope could be positive or negative. In the case of this equation here, E sub A is a positive constant. It's the minimum energy required for a reaction to occur. So E sub A is a positive constant, therefore the slope has to be always negative. At least always for this course. Oh. All right, let's do this question together. I know the answer was in the lecture notes, but could you please try to do this question now that we've, without looking at your lecture notes? Can you try to do this question, please?
Okay. I'm just gonna read it. Oh yeah. I realized so it's right
I have right here for us. So it will be K, right? I'm sorry.
So
what's the formula? That's just K.
K equal to
It's A to it's here. AE and then power to E negative. Yeah.
so I think we're gonna have to make two equations and make them equal.
Yeah.
So this one's gonna be K equal to 0. What's the value of A?
Well, no, why would you say it's going to be So, yeah. So, like, the temperature is 25 degrees Celsius. R is 8.314.
Well, the temperature was going to go 25 or 4?
So 40 times, food loss 40 times that, then storage for the decomposition of food. And then, like, avoiding that.
The reason I was going to make this. The reason I was saying because this isn't this going to stay the same because.
So then you do LMK and change it K.
So then you go LMK, LMK,
Yeah.
That's for reaction A.
Yeah, and then
Reaction 2, you go LMK.
But what's also the
I don't know, you go on to 2.
not necessary.
So then here we go. Combine. Oh, because this is the same for both. So we're going to have to go LMK
And then do the temperature for the
RT1 instead of it. I just moved that to the other one. Because here L and L and they're both the same thing. So we could take this and put it in there. Or you could do that.
Is that what you just said?
Yeah.
Oh, sorry. No, it's fine. I did that with that space.
But then you can't do this out because look when you're subtracting.
Yeah.
This can't do this. Right? Because you have this minus right?
Don't start yet.
Should we see it? Because here we're taking this minus this, so it's going to be LMK1.
Yeah.
I cannot hear you, Angela.
Minus that is 0. Okay?
Yeah.
So this is minus 1. And then that we're going to
Yes. No.
and then because these two, so then what do you have?
You don't need to know it.
Yeah, and then 1 over T minus. Yeah.
Got it on both sides. Isn't that what it is?
Natural.
See, what we did was, they went this minus this, but what we did was this. Does it matter whether it's temperature 2 minus temperature 1 or temperature 1 minus.
I mean, you got to get the equation right, but
Yeah. Because here they went K2 and that was but what we did was we went K1.
But it doesn't matter.
It doesn't matter. So you either go this minus this or this minus this.
Okay. Where did
No,
So it all depends on how you define here.
Oh, yeah. K2 is 4 times that. So this is 1, this is 4, that times more than this.
let's call this equation 2. Let's call this equation 1. 2 minus 1. What do I have on the left-hand side? 2 minus 1 on the left-hand side. ln K2 over K1 is equal to log of A and log of A will cancel. And then you have minus E sub A over R. And this is going to be 1 over T2 minus 1 over T1. Yes?
Why would E2 over the R be negative if we're minusing it? It's negative.
I'm just taking minus EA over R. That's outside. So this is 1 over T2.
I think it does. Yeah.
It's like saying something like this.
Yeah.
It's like saying, let's say this.
Yes, that's
For the negative E sub A over R, if we add,
Then you say Y. Excuse me, I don't.
or if we subtract another negative,
Why would this one make negative? It's like X minus.
I'm just doing 2 minus 1. So I have a minus E sub A over R. What's inside is 1 over T2. This becomes plus now.
Get your question.
but if you have a minus E sub A over R, and then that becomes a plus E sub A over R, wouldn't they just go to 0? Because you have a negative and a positive, it's the same thing.
No, but you're multiplied by 1 over T2.
Oh, okay.
Well, it's just like this. It's just like saying 2Y. Because here we have a different value.
Right?
So then you go 2.
Okay. Does everybody understand this?
Oh, okay.
Because this is different. So just like saying X and Y. It's like having 2 variables.
Oh, okay. Alright, that makes sense.
Okay.
Yeah.
It's like taking that one.
So now K2, let's say, is room temperature. So let's make this log of 40 is equal to minus E sub A over R. 1 over T2 is going to be 1 over 298 minus 1 over 277.